Right now, intelligence agencies across the globe are vacuuming up petabytes of encrypted internet traffic. They can't read your WhatsApp messages, your banking sessions, or your private emails, but they are hoarding them anyway, storing them in massive server farms. This is a recognized intelligence strategy called Store Now, Decrypt Later. The logic is strictly mathematical. Today's encryption is secure, but these agencies expect that a future machine will be able to solve the underlying equations. The data itself doesn't expire, only the secrecy of the math does. The scale of this operation requires vast physical infrastructure, relying on massive data centers operated by organizations like the NSA. They're absorbing global communications around the clock. A corporate acquisition discussed today could be highly valuable to a competitor 10 years from now. Those messages are sitting in a vault, waiting for the day the computational barrier protecting them is bypassed. To understand how these systems become vulnerable, we have to look at the specific mathematical problem they are built on. When you send a message, it travels through public routers and undersea cables. You and your recipient need a shared secret to scramble the text, but you have to agree on that secret without any eavesdropper being able to derive it. This diagram shows an elliptic curve, specifically curve 25519, the math that secures WhatsApp. By picking a starting point and multiplying it, drawing intersecting lines that bounce across the curve, you arrive at a final distant coordinate. That final destination is your public key, a number you can safely broadcast to the world. The system works because of a trapdoor function. Calculating the path forward takes milliseconds, but trying to trace the path backward from the public key to find your private starting point is called the elliptic curve discrete logarithm problem. Even if you used 1 trillion classical supercomputers running for the age of the universe, the computation remains unfinished. This extreme asymmetry, where an operation is trivial to execute but physically impossible to reverse, is the foundation of all modern digital privacy. WhatsApp goes a step further by using an algorithm called the double ratchet. Instead of using one key for a whole conversation, the system generates a brand new, completely unique key for every single message you send. The exact microsecond a key is used to encrypt a message, that key is permanently deleted from your phone's memory. This creates forward secrecy. If an attacker somehow steals your current key, they can only read the message you send right now. They cannot access anything you sent yesterday because those keys no longer exist. The result is a self-healing system. It ensures that a single compromised message does not reveal the history of the conversation, effectively isolating your data from brute force attempts. Every guarantee of privacy we just covered relies on one assumption, that any computer trying to reverse the math must test answers one by one. For classical machines, that rule holds true. On this chart, we see how a quantum computer rewrites that rule. Instead of processing bits as zeros or ones sequentially, quantum bits, or qubits, exist in a state of superposition. This allows a quantum machine to evaluate all possible 2 to the power of 256 values simultaneously. In 1994, Peter Shor designed an algorithm that weaponizes this effect. It uses a mathematical operation called a quantum Fourier transform. Through quantum interference, the algorithm causes all the incorrect values to destructively cancel each other out. Only the correct private key constructively amplifies, leaving a single readable answer. A mathematical problem that would take our fastest supercomputers billions of years is reduced to a task a quantum computer could resolve in an afternoon. We know the math works because we've already seen it happen. In 2025, researchers at Arizona State University ran a Shor-style attack on a real 133-qubit IBM processor. In 54 seconds, they successfully recovered the secret key from a small-scale elliptic curve. The target was a toy-sized key. Breaking the 256-bit keys WhatsApp uses requires overcoming the gap factor, the massive scaling disparity between today's 100-qubit prototypes and the millions of error-corrected qubits needed for a full-scale attack. The physics and the mathematics have already been proven. The survival of modern encryption is now entirely a countdown of raw engineering. Cryptographers already have the replacement. It's called post-quantum cryptography, and the new standards rely heavily on lattice-based algorithms built to withstand both classical and quantum attacks. This illustrates the shortest vector problem. Instead of hiding a secret on a curve, the grid rapidly extrudes into a 1024-dimensional space where the data point gets lost. This removes the hidden periodic structure Shor's algorithm relies on. The quantum shortcut simply doesn't exist here. The mathematics are ready, but the logistics are staggering. Every secure connection, every banking portal, and every messaging app has to be updated to these new algorithms simultaneously, all without breaking the internet's current infrastructure. Federal agencies are now forcing the issue. In 2024, the National Institute of Standards and Technology finalized the primary post-quantum encryption standards, officially kicking off the global migration. The intelligence agencies hoarding our data are not waiting for us to finish. Any delay in upgrading these networks means more of today's private conversations will be retroactively revealed by the quantum machines of tomorrow.